So hello everybody, so thanks for coming here today for a webinar where we will do some wizardry with C++20 with Joël. So as always, if you want to register for the school, do it as soon as possible because of course places are burning everywhere. So if you want to attend the school in Annecy, we have really few spots available right now. So please do everything to register and to confirm that you can attend the school in Annecy with an apartment, Airbnb, whatever. And we have also a lot of satellite sites now. We have 9 satellite sites for now, but I'm pretty sure that we will have some other in few weeks. So if you want to register, we'll be redirected to a satellite site near to you if you want to attend the school in a specific place to use a computing center, stuff like this. Or you can also attend online, as always. So we have a trailer to explain all of that to you.
Could a simple chemical reaction teach you how to unlock peak performance on today's supercomputers? Welcome to the Gray Scott School 2026, a free advanced summer school on high-performance computing. Designed for professionals from industry, public sector organizations, and academia. From June 22nd to July 3rd, 2026, join us in Annecy, France at LAP, at one of our satellite sites across Europe, or online via live streaming. All courses are taught in English. You can pick the courses most relevant to you or dive into the full 2-week program. You'll learn the practical behavior of modern hardware and how to write performance-optimized portable code. Week 1 focuses on CPUs, Week 2 on GPUs, covering architecture, bottlenecks, parallelism, memory, and performance analysis. All learning is built around a single challenge, simulating the Gray-Scott reaction. Simple to start, yet complex enough to stress compilers and expose performance limits. You'll explore modern tools, languages, and libraries such as C++ 17 and 20, CUDA, Fortran, Python, OpenMP, TBB, Kakos, PyTorch, and more. The school provides ready-to-use container environments for smooth hands-on sessions. Expert instructors from CNRS and CEA guide you with live Q&A and community support on Discord. Satellite sites let you learn together locally without traveling. Want to host one? It's easy with our turnkey setup, sharing the school with your colleagues and ecosystem. You'll leave not only with hands-on HPC skills, but also an official certificate of participation. And you know what? You can start early with 18 Gray Scott Thursdays webinars, weekly from January 29th to June 11th, introducing summer school concepts and new topics. Whether you're an industry professional, engineer, researcher, or student, if you have programming experience and want to push your skills further, this program is for you. Register now at cc-fr.eu and start learning today. Gray Scott School 2026, Europe's leading HPC summer school.
And if you have some question to register or to become a satellite site, you can send a mail to Karim, to Marie, or to me, and we'll be glad to answer you and to help you to be sure that everything will go according to plan for you for the school. So today we will have Joël. So Joël is involved in the Gray Scott School since 2024, in fact. So you start to develop Eve So we'll talk a lot about that also, with maybe a bit of Kiwaku today also.
I will see.
Okay, so I will not spoil too much.
Depends on the time.
Yeah, yeah, we have a bit of time, so I will not spoil too much, but you will see that doing some vectorization, but with smooth implementation is not really easy, and it's and you don't want to rewrite it, of course, so you want to reuse it as much as possible. And so, as always, if you have some question, please use the chat. We will answer all the questions at the end of the session. And without further ado, Joël, it's up to you, and I wish you a happy webinar.
Okay, thank you. Thanks everybody. Hello. So I'm Joël Falcou. I'm associate professor at what is it now? Université Paris-Saclay. Last time I checked. I'm also the co-founder and training advisor at Quadricons. So it happens that we do research, and we do research about how to write tools for people that want to actually get some performance out of their wonderful machines that we have today. And among all the things we deal with, one of our well-loved projects is Eve, which is aimed at providing a great way to simplify the design and implementation of manually vectorized algorithms. I will say it again, but I like to say it right now. Obviously, this is it's a long job. It's a long team job. This is the name of few people that currently contributes. There is a bunch more. I should have updated this slide now, but yeah, it's a teamwork, and I want to emphasize on that. So what are we going to speak about next to that? So the thing is, I need to click into the correct screen. Okay. Yeah. What are we going to speak about? You are probably used to the fact that your processors is basically a machine that consume data and instructions in order to produce results at a given path. Okay, it's a bit more complicated than that, because you can have multiple arithmetic and logical units doing different things. You can have micro instruction getting turned into more complex things. You can get out of order and whatnot. You get pipelines. So a lot of things still happen in this simple CPU design, but if we strip out everything, at the end, you have a single flow of instruction, you have a single flow of data, and you produce a single flow of output. Okay? That's what we call the single instruction, single data model. Okay, that's the name of that. Turns out, if you got spare transistors and you don't know what to do with them, you can go a bit further than that by keeping the single flow of instruction, but by consuming data in a different way, namely by consuming multiple data per instructions. Okay? So instead of having one register or a couple of registers containing the data and getting processed, you will have what we call wide registers, okay, that contains multiple values. Okay, so we are going to see it started a long time ago with 64-bit registers. We are now up to 512 bits. So we have more and more elements per those wide registers, okay, that get consumed as if. So we have a special or multiple special computing unit in those processors. And then you can actually use those units to do those computation in parallel. Okay, so it's a classic case of embarrassingly data parallelism, and that's exactly what we want. And the question is, I mean, where do I find that? Well, basically, as long as you don't time travel into the 70s, basically everywhere. If we want to go back to the original SIMD things, we are going to go back in 1994 with the HP Max processors. But if we want to stick to things that people actually used, I mean, it started with SSE and SSE2, and even if we goes back to this MMX, okay, back in the end of the 90s, x86 Intel led most of the development on this front in the customer side processors. We had a bunch of 128 bits extensions, so their goal at the beginning was to accelerate multimedia computation, like those very important tasks we did in the 90s, like decompressing a JPEG or listening to an MP3. And as the name implies, they were using 128 bits registers. That means that a single SSE register was, for example, able to hold 4 floats at a time or up to 16 8-bit chars. Okay, that means that if you were doing like, I don't know, like numerical computation, you can get some kind of speed up of about 4. And if you do it quite well, if you were doing like 8 bits based image processing, for example, you have a potential times 16 speed up to get from there. Okay, obviously it's not as that simple, but that was the order of magnitude of what we could get. Okay, and we are back in the 90s, so getting 4 times faster is actually a big deal because we didn't have multi-cores back in the day. Okay, so that means that you could actually save on a bunch of processors. At the roughly the same time, after SSC2, Motorola, IBM, and a bunch of others designed the Altivec PowerPC extension. That was one of the reasons why the PowerPC enabled Mac machine back in the day were that powerful. It's a different design, but it's the same idea, 128-bit registers. And during the 2005-ish, something like that, Intel went with a bigger register size, 256 bits. Then a bit later with 512 bits, okay, which is basically where we are standing up right now. Another player came around, ARM, with the Neon extension, and the ASCMD, which is basically 64 bits enabled Neon, with 120 bits registers. Again, same vibe as Altivec or SSE. And recently, with the SVE and SVE2 extensions that can climb up to more bits than that, theoretically up to 2048, but nobody does that. SVE is a bit special. We are going to speak about it very few, because for maybe the oldest of you in the audience, it's more like a vector machine than an SCMD machine, so it has a bit of a difference in the way they do this, but it presents the same way as special register, special operation, and then we get speed up. The newest comer is RISC-V, which has a bunch of SCMD-enabled options. Okay, you can do SCMD in the web browser using WASM and so on and so forth. So it's something that was huge back in the 90s. It fell out of scope for a while because people were mostly focused on other things like multi-cores and GPU, and now it came back because it's a bit silly to let this times 4, times 10, times 20 speed up on the table and not using them. Okay. Yeah, okay, fine. I have a bunch of architectures to deal with. Is it good? Is it bad? Well, it's good because you can pick up a processor and you probably have a SAMD on it. That's a good part. The worst part is that if your job is to actually design a simulation, a software, a tool that has to be able to run on, let's say, only 2 or 3 of those things, it starts to be a mess. Because, of course, there is no standard behind that. Okay, so every vendor has its own specific things, and we are going to see that in a bit. Why do you want to do that? Because, you know, we have GPUs, we have like the clouds, we have the whatever. Okay, well, sometimes you can't use GPUs because it doesn't fit into your product, because you don't know if people will have the correct GPU to get the correct performances. Okay, SIMD chips are basically everywhere. I mean, if your company / research center / lab has machine without SSE 1 in production, it's time to find a new company, if you see what I mean, or get some money to get new machines. Okay, and it's also less energy demanding, which starts to be a growing concern. Okay, so yeah, okay, how do I exploit this? Because by the way we see that, I mean, special registers, in special operation, in special part of the CPU, well, smell like a work for the compilers, right? The compiler is all about turning our proper code into something very specific for a given architecture, and it does. It does. And let's start by being very clear. Autovectorizer nowadays, on a large number of simple operations, they do great work. So most of the time, you're probably already using SIMD without knowing about it. But they are very, elusive creatures, so autovectorizers. So as soon as your code looks a bit strange, or you speak too loud or something like that, they stop working. So when they work, it's good, and you should just stop there and go on your merry way. But sometimes it doesn't. It's not enough. So we have other things like you can use OpenMP SIMD pragmas. They kinda work, but sometimes they kinda work like the autovectorizer. So okay. But you can actually explicitly ask for the vectorization to go down. You have special compilers with special notation. One of the most prominent is probably SPC. Inside the language itself, you have a bunch of things. So you can have a look at the unsec execution policies on C++ algorithm. Okay, that's something that happens. You can use library like HPX that basically wrap up that in a different way. As of 2 weeks ago, in Croydon, we voted for C++ 26 latest additions. That includes STD, SCMD. We are going to speak about that later. Let's say it this way, in a tongue-in-cheek way. It's basically if but worse, but it exists, so we have to discuss that. You can also use specialized libraries. That if you know that you are doing one very specific task and nothing else, probably people already vectorize such things. Okay, so you can use stuff like LAID if you are into image processing. If you want to get very fast JSON parsing, you can use SIMD-JSON and whatnot. Or if you are desperate enough, or you can do it anywhere else, you can write your own SIMD code by hand, which is well, not recommended somehow. So let's take a very simple use case. Okay, let's do a times b plus c is 32-bit integer. Okay, right? Let's write that. Okay. In SSE2, you can do it. I'm not putting it on the slide because it's probably 3 slides long. Okay, because we have no way to do this operation in SSE2. What you can do, however, is do this exact same operation using 16 bits integers. So if you remember what you learned in the kindergarten school and whatnot, yeah, you can put down the operation and write your 32 bits operation as a sequence of 16-bit multiplication and addition. Okay, yeah, you can do it. It's not fun. Starting SSE4, we have something better because now we have an actual 32-bit multiplication that gives you the low part of the result. It's exactly what we want. So you can actually write something like this. Okay, you do the sum, okay, and you do the multiplication. And if you want to have a look at doing that on AltiVec, because you need to support PowerPC for some reasons, okay, first things first, types are not the same, so we have to wrap that somehow. There is no multiply add on integers. And so one way to do this is to basically convert your integer into floating point values, doing FMA on that, and going back to integers. It will work up to the point when you try to add and multiply something that give you something that is not correctly representable in the floating point numbers, and then you're screwed. So it's not easy, actually. And we could keep going on that over and over. And every time a new SSE extension goes out, every time a new variation of AltiVec goes out, you get a bunch of other operations, but do they fit what you need? Maybe, maybe not. A good metaphor for that is you are given a box, those beginner box of Legos, the one with the bright colors, with all the red and the yellow and the green and the blue. And your task is to build the Batmobile, okay, right, in the gray, okay? So how do you do that, okay? How do you fill up the gap of the missing operation into the hardware? For the longest time, people were doing that by hand. It was a tedious process. People found out some tricks very late into the game. I'm going to speak about that a bit later. Some of those knowledge is probably lost to time because people never wrote them down public. Okay, so they get rediscovered again and again. Yeah, so it's a mess. And it's not a piece of code you want to have in the middle of your actual logic code. Okay, nobody wants to see that. So you want to hide that somehow, because it's not feasible if you want to do this at scale. So that's exactly what we wanted to do with Eve. But before talking about the current state, okay, just a bit of history. Eve was actually started as a very different project back in 2008. Well, 7 actually, but 8, let's say 8. It was a wrapper around AltiVec and SSE2, so you can write the same code with both of them. And it was hidden inside another bigger library that was doing like array-like computation. At some point, we extracted it out and we started filling up the blanks. It went dormant for a while for a bunch of reasons. And then we resurrected the project back in 2018. And yeah, we are at it since then. Okay, so it's an old project. It left, it rise, it fell, it rise again, and so on and so forth. So currently, we are a C++ 20 library, okay, that try to find a decent way to abstract the management and the computation around SIMD operations. So we have a library of core types that encapsulate those vectors things. Okay? A bunch of algorithms in the sense of a standard algorithm like construct, And well, it's probably more than 300 now, but a bunch of math function and numerical functions. We basically work on everything x86 ARM, 64-bit ARM, PPC. We have a in progress support for WASM and RISC-V. WASM is basically working, but the test doesn't want to compile, but that's another issue. RISC-V is still ongoing. We are using a Boost license, so you can take it, use it, and do whatever you want with it. If you do use it, please send us a postcard so we know someone is actually using it. And as I said, it's a team effort in random orders of importance. Denis actually worked out most of the newest algorithm systems we have now. Jean-Thierry Lapreste is our math guy. So if you ever use a function with a strange name inside Eve, it probably is. Alexis is working with us as a PhD student. He's working on the 16-bit floating point integration, and I do whatever is left. So you can find us on GitHub. Is this working? Yes, it's working. In the very, original places you can find it. Okay. We have some documentation that we try to get nice. Okay. So a bunch of tutorials. You have it's a doc, okay, and we try to let's pick a random one. So we try to have something, okay, legible with some kind of usable examples. Okay, we try to be as comprehensive as we can on the documentation. Okay, and if you go on Compiler Explorer, we probably have the trunk running around, so you can actually play with it without having to install it, even if it's trivial. So yeah, that's the thing. Let's just see what we can do, and we are going to dive into the details, but just this kind of operation we can get there. Basically, this is a manual vectorization of Sterlen. Okay, so we get a string as a pointer to char, and we try to find the size. And if you think about Sterlen, it doesn't sound like that's something that looks like it can be actually easily vectorized, because you don't know where to stop. Okay, so you need to consume data, but what do you do? Turns out we can, because while are just badly disguised for loops. So if you massage them enough, you can vectorize those. And so basically what we do is that we are going to load a bunch of data, trying to find the zero inside. Once you get the zeros, if you don't have zeros, you keep walking up until you find the match. And when you get the match, you can finalize the computation. Okay, well, we have a question.
The question is from Sergey. So classical math functions like trigonometry, hyperbolic, numeric flow, etc. are about 20, 30. What are the other 200 functions that you mentioned in Eve?
We have, basically we have the whole CMAT gallery. We have a bunch of extended operators. Okay, we have a bunch of conversion functions, because conversion in SIMD code is a bit tricky. So you want to be able to specify exactly how you want to convert your data. We have a bunch of IEEE 74's helpers, like the equivalent of FRX, LRX, and stuff like that. You can actually also have a bunch of predicates that let you optimize some operations on what's the value you have as a property, because some of them are not present in the scalar versions. And we have a bunch of, as you said, logarithm and whatnot. And what we do, we also have also special function gallery like Bessel and whatnot. We have a bunch of SIMD specific operations like scan reductions and other internal SIMD register computation. And one thing we are going to discuss a bit later, or maybe trigonometric is not a good example, but let's have a look at that. Our functions are actually more like function hubs. So the cost function is actually a bunch of them, depending on how you want to get your results, which type of input and output in terms of degree radian and whatnot. We have a bunch of specific precision speed trade-off markup. So you can ask for a very specific function with a specific performance profile. Okay, they register as a single function, but that's basically different implementation. And so we have all of that, and we also have a bunch of function-like operators. So plus, minus, and whatnot also appears as a function, because you can apply stuff like saturation, modulo operation, and stuff like this. We support masking, but masking is something that doesn't count. So basically, another way we could have written that would to have a cos-d function, a cos-phi function, and then have a fast cos and whatnot, but then all gets punched together into a single AP point. Okay. And we probably have a bunch of, also I forgot about that, where are they? We have a bunch of shuffles. They are not all there. Someone didn't want the doc, sorry. But so you can actually manipulate the CD register as its own and so on and so forth. So yeah, I mean, I probably have to recount, but if you put all that together, that's basically the count we are. I mean, if we go by the number of unit tests, we are practically there. That's a good question. Thank you, Sergey. If we look at this simple example, we kind of see a bunch of the basics. We have this wild type we are going to speak about a bit later that embodies this architecture agnostic SIMD registers. We have a bunch of memory-related helpers because SIMD programming likes their memory aligned and whatnot, so we have some helpers for that. And then we load some data from some memory. We try to find some information. So basically, this is something that say, okay, let's see if there is any zeros in the block I just loaded, and give me the position of the first true in these predicates. Okay, and so if there is no true, I'm going to keep up walking down the data. As soon as I have a match, I'm stopping, and I can get the value of the match that will contain the index of the first zero I got inside, and I can do some fancy, pointers, arithmetics to get to the star length. This is the same code. That's the important thing. This is the same code, whatever architectures you are going to target. This is working on x86. It can work on ARM. It can compile on PowerPC and whatnot. Okay, and if I go there, I mean, this is the thing. We can have a look at the simple SSE2, I think, operation. So we basically end up with something where at regular level of optimization, right, is basically, I mean, nothing is left. Okay, so only those fancy register going up. You got the fancy masking comparison going on. And then I can use AVX2. AVX2 has bigger things and it has a more compact way to do the comparisons. And if I want, I can go up to AVX512 and I will get the new way of handling the mask, which is basically having special register for that. And we just generate the same thing. And this is a very important core principle into if the architecture you target is chosen at compile time. We have a bunch of tutorials if you want to have multiple architectures in the same binary, but for performance purpose, the target architectures is fixed at compile time. But obviously, I mean, we are going to see that can do a bunch of things in the different places. But the resulting code is basically what you have. I think we have a small benchmark a bit later. These Sterling things, if you manage to change it a bit, but not by much, we are basically outperforming or being on par with optimized libc Sterling, so it's okay. But we didn't write any assembly, so I'm fine with that. So let's go into the actual meat of the things, so we can get a look at that. So the basic thing is wide. So wide is an abstraction over SIMD registers. Basically, you are asking for a register of some types with a given number of replication, what we call number of lanes. Okay, so this number of lanes has to be, as of now, a power of 2. Okay, and basically you can actually ask for a wide of whatever, like we do there, and you will just adapt to whatever you compile. But you can also specify the lane count. It's a bit less portable, but sometimes you need to do that. And the system behind that is made so that if you ask for a number of lane that is, let's say, bigger than what the actual type on your machine is supposed to handle, we are going to silently turn your register into a bunch of registers, and we are going to basically unroll your operation. So if you are on a AVX2 machine, your register of double has 4 elements. And so if you ask about 16 of them, for example, you will get a bunch of 4 registers like that. It's actually very helpful because it lets us do a type to type with same lane count conversion. So if you have like 16 char, you can turn them into 16 floats, which happen to be 4 pack of 4s, and it's transparent for you. If you ask for less, so you have you want to have a wide of 2 floats, for example, instead of 4. We are still going to use a vectorized register, but we are going to ignore the part you don't use. There is also a special source into the template definition that makes you unable to do mistakes like writing a function that waits for a wide of int, export it as a shared library, and use it on another hardware. Okay, it's not going to work. It will see that it doesn't fit. Okay? And every function and operator just work on them as if they were scalar values. Okay, and they yield the proper result in every lane. Okay, so we have a bunch of ways to construct them. So you can build them from a constant, so you put the same value everywhere. You can pass a lambda. Actually, two types of lambda, one that take an index and the size, one that just take an index, and you can fill up every lane as you wish. You can load data directly from memory. And as I said, you can specify the lane count if you want. Okay. And everything is statically asserted so that you cannot have a stupid number of lanes. You cannot use types that doesn't make any sense and whatnot. In terms of types, we handle multiple things. So the regular types like float, double, all the integers and whatnot. We handle the enums. So you can have like an enum of some types, and we are going to fetch its underlying types and make it works. And we also support structs and, tuple and tuple-like struct. So what do we do? So we have every basic operation you can find about. So if there is an operator that do it, we have it. And as I said, we have function version of each operator that help us get some additional operation. Okay, on that. We have fully vectorized CMAT. We have a huge set of special and similar function combinatorials, best and whatnot. We have a bunch of polynomial evaluation scheme. We have operation over the registers themselves. Okay. So how does it work? Every function are actually a callable object. It's not a template function. And so we can actually do funny things with that, okay? Including masking supports, option supports, and easy combination of them. Okay. So yeah, this is the kind of thing we can do. So C equals C+4 is basically what we think it is. Add is the functional equivalent of plus, so we can actually put option on it. Option are passed using square brackets. And so what is this? Basically, I'm going to do C+4, but only in the lane where A is actually less than B. Okay, so it's a conditional operation. Depending on the architectures you are targeting, all right? It's either a specific intrinsics, if it happens to exist, or we try to emulate it using the correct, fastest way to do that. We can also have a positional mask, like this ignore first thing that will perform everything everywhere except on the two first elements of the lane. For other computation, we have also semantic options, like you can ask for saturated operation, you can ask for pedantic operation, which is basically a slower version of the algorithm, but it takes care of special cases, like usually the normals, infinites, special values that may diverge if we are using the original operators and so on. You have the numeric modification that basically ignore non-numeric values, so it skips nans and so on. And we have the raw modifier that basically says that you want to go as fast as possible, you don't care about the precision, right? No error checking, fastest implementation we can do, and so on and so forth. So we can also combine the operations, okay, right? So you can skip the first elements and ask for a row, square roots, and whatnot. Okay, they can do that. The day we move to C++23, obviously it will be a single bracket operator, but that's basically what we have right now. Depending on the operation, you may have special semantic option. For example, the trigonometrics has special options for handling the range of whatever the angle you are computing. Some polynomial evaluators also have special options that relate to the way you want to do your operations. And this is all done because we have those things as object, actually. So another important thing is the shufflings and swizzles. When you deal with some operation on registers, on wire registers, sometimes you can get very good performance by actually loading the data easily and reconstruct the data you need to compute by moving pieces of the registers themselves. So either you can have what we call name swizzle, so that function with a proper name, like reverse, take your values and put them backwards. You have broadcast, you have like interleave and stuff like this. Okay. Or you can pass an arbitrary pattern that can be either a list of index, okay, that's not very portable because of size reasons, or you can pass a lambda that will compute the permutation, or it's not a permutation actually, the rearrangement of the data you want, and you can pass that through the shuffle function. And this is usually something that is very efficient on almost all architectures. especially the named one. We have a funny way to map your lambda patterns to the named shuffle if it exists. So if you accidentally write reverse like this, okay, we are going to see, okay, yeah, that's the reverse. Let me call reverse, if it exists, instead of doing the whole manual shuffling things. There is work in progress on that. We still need to have a decent API for multiple wide shuffling. That's something we are still working on. And we are trying to optimize the compile time of this monster, but it works. So how does this work? A typical if function has a bunch of overloads, depending on types, architectures, options, a number of parameters sometimes. And we want to be able to find the proper, most efficient combination of instruction depending on these things. Okay. Some assembly instruction and types doesn't work. We need to emulate them. Some architectures doesn't even have the types at all. Okay. Altivate didn't have double for the longest time. And sometimes you need very specific optimization inside your optimization systems so that you can actually get to the proper numbers. So we do that by having a layered system where basically we use C++20 concept to select the architectures. So we already have, cleaned up a lot of the trees. And then we are going to categorize the types we are working in and use a cascade of if const expert to select the proper implementation. Sounds like a lot, but it works. So basically we have this giant funny function called ABA_off that basically takes a type and the number of lane, look at which instruction set you are aiming for, and will tell you what kind of ABI you should be supporting. And this ABI marker is a newsletter to select there in the function itself to select which actual set of overloads we are concerned about. So the first thing we do that we are going to take care about only the architectures you are on. So it removes a lot of overloads. And then inside this, we have this categorize function that tells us what kind of things we have in our vector, okay? What kind of types and how many times we have it. And, I don't have it on this example, but you can have stuff like wide category, large category, like it's any integers, it's any pack of 8, stuff like that. So you can actually select the thing. So, and for example, in this case for add, what we just do after that, we just annonate every possible combination of things. Okay. Sometimes you have to be careful about that you are currently compiling for at least that or these architectures to have access to some of them. And we have a way to gracefully cascade into an emulation layer later on. It sounds like a lot visually, it is, but most of the time it's either just that, a cascade of if const expert, because that's the best thing we can do. And as soon as you go over a given layer of complexity, you just call other function, and it's all of that is transparent internally. One thing we learned, and that's probably important if some of you are currently dabbling with C++20 concept and whatnot, concepts are good at selecting a bunch of overloads for some reasons. But sometimes if your code selection is more like what kind of implementation do I need instead of an actual algorithmic or architectural reason to select an overload, if const expert are actually better. Okay. And so we have this 2-tier system of concept for the ABI and then if const expert for the actual implementation and optimization. It works well, it's easy to follow, and it's still better than having I think add has 50-something implementation just for x86. So it sounds better than having 50, function overload or whatnot. Okay, so yeah, that's the great scheme of things, how it works. Now let's see what we can do a bit better, because slapping, intrinsic one on top of each other is fun, but at some point we want to do computation, okay, right? So you could actually write your loops by hand. We provide everything you need to do that, but sometimes what you are writing is actually just like a transform or a reduction or maybe some kind of pseudo standard algorithm, right? So what about providing SCMD aware guaranteed SCD-like algorithms? Okay. So that's what we do. We have a bunch of them, not all for some reasons. They support options also, in a way so you can actually tune them for some precise purpose. And we know how to interact with complex data structures. by providing different way to interact with array of structure and structure of arrays. We have algorithms, we have views also. We are basically a SCMD version of the range library, okay, as much as we can. And we can try to write stuff like that. They basically work like a range thing. So the API is basically what you expect them to be. So let's focus on the performances, okay, right? So I'm trying to find the zero in a block of 1,000 bytes, okay? So the size in bytes is fixed, okay? And so the blue line is the time spent by ST-defined, full-blown optimization, fast math, whatever you want, okay? Depending on the types, okay? So 8-bit, 16-bit, and 32 bits integers. So obviously we go faster as we go with the biggest types, obviously, because we have less iteration to do. The funny thing is the SIMD version is basically flat down there. It doesn't depend on the types. It depends on the size of the vectors. Okay. And that basically is the best we can do. Okay. So we are, how much is that? I think we are like, this is AVX2. Yeah. So we are basically 6 times faster on integers and about 30 times faster on char, something like that. And so that's cool because finding a zero is like basically half of what Sterling does, for example. So we are pretty much there. ST-defined is actually being mean because ST-defined do a very more generic code than what Sterling does, but it's basically where we are. We can also do some funny things, like vectorizing remove if. So for people that doesn't know remove if, yeah, you have a segment of data in memory, okay? You have a predicate, and what you want to do is to remove the values that fulfill the predicate. So you want to remove all the negative values from your table. But you don't let them become a zero or something. You actually compress the data. So if you have like 1 minus 2, 3 minus 4, the end result is 1, 3, and some garbage in the memory, but the algorithm give you back the zone where the correct value are. And if you say this way, doesn't sound like something you can actually vectorize because you are going to move pieces of values. There is no way I can do that by block because I don't know how many things in the Y is going to be removed or not. Turns out actually you can because there is one operation that came up into AVX2 and then later ARM. That's basically what we call a compress store. Okay, you give it a value as a Y, you give it a mask, and it will store the value for which the mask is true. Okay, so basically you can use these compress store things to write remove if in a vectorized way. And so this is the funniest graph we have there. So the x-axis is actually the percentage of values that fulfill or does not fulfill the predicate. Okay, so at 0%, everything is untouched. So it's basically a copy. And if we are 100%, everything is wrong. So it's basically doing nothing except skipping the data. And the worst case scenario for the scalar version is the 50% range. Because that means that every 1/2 elements is going to be removed or not. And you're basically trashing your branch predictor. Okay, there is a branch in it and it just keep going that. And so that's give us this big pyramid things. Okay, the blue one is char and so on, and we see that the integer is very small actually. And in our system, the vectorized way, basically what happens is we are going at the same speed every time because we are just roaming over 100 or 250 16 bits at once and just do a branchless algorithms. Okay. And so it's basically a times 25 over the char or something like that. Okay. So we can actually vectorize complex algorithms as soon as you see how we can actually do the things. And when we were designing the SIMD algorithms, what we did was try to find a way to make it work, and then work back the API back. So we have something that is efficient. For example, our reduce algorithm is a bit different than the standard one because if you want to be efficient, you should not. Sorry for what I'm going to say. std reduce take a function to operate over the values and do the reduction. But if you want to go to be efficient in CMD, that's not a function you want to pass. You want to pass a monoid. Okay. So you need to know about the bunch of properties of the function, namely its it's a neutral element and a bunch of things like that. So we have a way to build those kind of things, or an abelian monoid actually. And so we know that it's correct. Okay. And if you pass us a function, we automatically devolve into the slow version of the algorithm because we cannot do better. Okay, so fine. A bunch of algorithms. How many? A lot. I think the one we don't have right now are the sorting one and the partition one because they are very tricky to get right. And especially sort, because STD sort is a monster in itself. And to be able to consistently win over it, it's a huge amount of work. Okay. There is a bunch of papers about having a dyadic system of filtering stuff to do STD sort. We will still have to have a look at them. So we can do a bunch of algorithms like that. But we can also use them into a funny interaction. So let's do some basic high school physics, okay? We have a ball, okay, that falls over under a gravitational pull, okay, right? A ball has a position, which is its z-axis, basically. It has a speed, okay? It has probably, what does it do? It doesn't even have a mass, okay, right? I mean, the mass is 1 or something. And there's some elasticity, okay, so it will bounce harder or lower than what it does. So we have this function, okay? It takes a time and space, it takes a gravitational constant, and take a B, which is like a ball. Okay, we are going to see what it means. Ball is a struct, okay, we defined, and we adapted to so that Eve can see inside it. So we are taking anything that behaves as a ball. Okay? It can be a ball, it can be a wide of ball, or something that was a ball but is not a ball right now, but has a proper components. Okay, and ball come with a bunch of function, position, speed, elasticity that extract the correct members we need about. So we have them the position, we have them the velocity. We do that like Runge-Kutta doesn't exist or whatnot, and we compute the new speed in case the ball is bouncing. And how do I know which value I need to use? Do I need the falling ball or the bounced ball? We are going to look at the falling ball position, and if it's close to 0 enough, we probably just hit the ground. Okay, and so in this case, we are returning the bounce value. Okay, that basically just swap the speed vector, and if not, we continue falling. Okay, and these things, not sure it compiles right now, but let's have a look at that. Does it? Probably does. It does. Yeah, it's a bit long, but it does. Let's have a look at the code. So the ball is basically a struct, and we say that it's something that Eve understands as being a struct, okay? For people following at home, yes. C++26, reflections, we are going to amend that later, but for now, it's this way. So ball is basically a triplet of floating point values, the position, the speed, the elasticity, and counter, which is the number of times it bounced, okay? And we have functions that give us whatever we need out of these things. Okay. So this is our update of the simulation step. It's basically read like a bunch of maths, nothing else. Okay. So we added that. I mean, we count the number of bounce on the bounced balls. Okay. And now let's run the simulation, right? So what do? We take the gravity, the time, the number of maximal bounce we are allowed to have. And we take this thing, SOA vector of ball. Ball is a tuple-like struct that we adapted through EV struct supports. So we know how to deconstruct it into its pieces, okay, right? And SOA vector basically take one of those types and basically do the array of structure of array conversion, right? So everything inside SOA vector is actually a vector per members. It's easy to vectorize and whatnot. And so what do? Well, we are going to call transform in place that takes my vector of balls, my behavior function, which is this one, the update class with whatever parameter we need, and we update the thing. And then once we update, what we are going to do is we're going to remove every ball that bounce too much, because we don't want to keep doing that. And once I remove them, I know exactly where to cut, and I clean them up from the balls vector, and we keep doing that every time we want. let's have a look at the assembly, okay, right? So inside the simulation, what is interesting is, where is it? Yeah, it's there. Okay. So what do? We do a times a times b plus. We do a minus. We have another multiplication, and we have an if else. Yeah, we have a mul, a add, a sub, a mul, some comparison, a if else that we mask, and then we subtract the things. We put back everything else, and we do it again. One block, second block. Why? Because we ask explicitly to unroll this algorithm by a factor of 2. If you don't say that, we have some kind of an heuristic that tries to know what kind of unrolling we can do, and it's very simple. Like if the function is known and simple, it's 4, and if not, we don't do anything. But you can control that. And we see that we have the computation there. We have some sort of a computation there with a single pass. And then we have the scalar one later on, because what we did was trying to find a way to use the fact that we know that SOA vectors are aligned, so we tried to align the thing, and then we finished by doing something like that. And yeah, and that's all. I mean, and you can actually see that the core computation is basically what we expect. Let's see if I can do something. Oh no, it won't work. Let's see what happened if I was like in a lesser architecture. Okay, let's see what's going on. So I just changed the compilation flags. Code is the same. Okay, I could actually have run that on the ARM processor also, but I don't have one there on this machine, so I'm going to pass. Yeah, so the code is a bit different because we don't have the same operations, right? But we see that we do the mul, add, whatever. We are in the smaller register. Another thing we can do if we go back to LX2 is to try to use the FMA of operation sets. That gives x86 a bunch of 1 cycles A times B plus C without any intermediate rounding things. And yeah, do we have? Yeah, we don't. We don't because we don't call it actually. So let's see if we can do something like that. We can say that the position is so the compiler doesn't want to do it. Oh yeah, I cannot edit that. The compiler didn't see it for some reasons. Okay. So what we could have done is to actually call the FMA function that ensures that if you have a FMA function on your system, we are going to use it. Sometimes the compiler go back in our back and turns that into an actual FMA. It probably doesn't do it for some reason there. But if you really want to be sure, we have the function to be able to do that. But the cool thing is we've wrote something that basically looks like maths, physics, whatever. Okay, and we have a bunch of algorithms in places, and we got the actual optimized code going on. Okay, this is the kind of thing we can do. Okay, right? And using struct as something you can actually vectorize all by themselves directly is very important. Okay, that you do a lot of things. So we have this system support for that. It's going to evolve because we want to make it simpler. But basically, you can actually do SIMD computation over data structures, okay? As long as they behave like a regular structure. I'm not going to go too much on that, but this is something we didn't write. Okay, this is part of a library called Airmax, which is database system. Okay, and basically the people from there wanted to accelerate some of their computation in the database. And so one thing they do is you have a bunch of data, and you want to know in your database which lines, what are the line index of the data that verify a predicate. You don't care about the data. You want to know that on your 10,000 lines of database, line 7, 25, 63, 29, and whatnot, contains the values that fulfill the predicates. So you are going to say, yeah, I can see how I can vectorize the predicate actual, application, but how do I do this I want the line number instead of the values, right? And I want them compact again. Okay, so turns out you can. So what do? Yeah, well, we start by putting the index vector back to 0. We know that at most, we are going to have as many values in the index array that you have values, obviously. We put a bit more data set behind for optimization purpose. We are going to go about that a bit later. So then what do? Well, you generate a view called IDXs, which is calling IOTA. IOTA is basically lazy evaluator for 0, 1, 2, 3, 4, and so on. And what you do is that you take your value from the range and your iota and you turn it into a local lazy structure of array things. Okay, you zip both of them. Okay, and then you go over every pair of values and index. Okay, and you say, okay, let's get the element from the pointer to the things. Call the predicates. Give me a mask, and I'm going to compress copy the mask. Okay, with a bunch of options, okay, into the output. And what do? I use that as a value I copy back. I don't copy back the value from the element, I'm copy back the associated index. Okay, and when I'm done, I am at some place into the memory because I advanced it, okay? So compress copy returns you the shifted pointers. So after this for each, right, I know where I'm stopped inside the data. Okay, and so I can resize the actual result by computing how many elements between the beginning and these pieces I have, and then I shrink to fit because I don't want to have laying around memories. And this thing on AVX2 on 64 bits integers, okay, for indexes and values, gave them a 3.5 speedup out of 4. And the code is actually okay-ish. I mean, it doesn't have any leak from the actual underlying architectures, right? And we have something that, I mean, is sort of understandable. I mean, we have the element, we have the index that goes with them, and we are applying the predicates on the element, and we are going to store them only if they are fitting whatever we are going to do. And what do we store? We store the index. So it's a non-trivial operation when you think about it. I can tell you by looking at the bench those guys did that the auto vectorizer is completely like not there, okay? Because the original, you can see what the original code in scalar mode will look like. You have a bunch of ifs and you have a bunch of breaks into the loop and whatnot. Okay? So it's completely lost. And we managed to turn that back into something that can get most out of the system. Okay, right? One funny thing, so for each is completely different from the standard because for each takes the lambda that takes the pointer, the iterator to where you are in your data, and the mask. This mask is usually true everywhere, most of the time, except for potentially one place, which is the end of your data. Because you are going to mask the data you can't reach from your vectors. And what you have to do into your function inside for each is to process those data and the mask and do something with that. Okay. But basically it works like this. And if you see for each is actually there, it's an object we built from the algorithm for each by putting some important optimization options that we don't want to write more than one. So it doesn't handle alignment. So it's all unaligned access. And the function is big. Compress copy is a big function, so we don't want to have any unroll. Okay, we could now use no unrolling as a shortcut, but that's basically the idea. And then we call this algorithm we specialized over those data, right? And it works quite well. So now let's conclude a bit of all of this. Why do you want to do that? Why do you want to manually vectorize codes? Because sometimes that's the last option you have. Okay. Either because the compiler you have is not able to see that your code is actually data parallel, because your algorithm is very specific yet vectorizable, but you need to vectorize it by hand because the compiler is not going to do anything. Or sometimes you know that you have this times 4, times 5, times 10, times 16 or whatever speed up and you want to get into. What Eve tried to do is to simplify this. I mean, it's not an easy task because it has some algorithmic interpretation on that. But yeah, it's something we want to manage. So if you want, you can actually try Eve in your code. We still have a fluctuating API, but we try to do that properly with tag release. I'm seeing that and I forget to make a release this year, so blame me, but we are going to do one. Is there bugs? Maybe. Let's be frank. The API surface is quite big. We try to have a huge amount of unit tests, but maybe we forgot something. Recently, when we started to work on the 16-bit floating points, we found out that some of our tests were a bit over eager of accepting some values, so we had to fix them, the function and the test. You don't find the function you want, you work on a very specific architectures we don't support. Yeah, I mean, we are open, drop a PR, drop a issues, and we can discuss that. The workflow we recommend is to try to find the biggest offenders. I mean, I don't know if it was done already, but you probably have already a webinar about finding hotspot and whatnot. And if not, it's probably one at some point, or you can have one at the school. Let's focus on that and try to extract your logic into something you can optimize, and then you can put it back. And if you have any issues, you can just drop us a line, and one of our collaborators will probably have to have a look at your code. If you have very specific algorithmic problems, Dennis will probably nerd out about it. If it's math, it's more like John Terry's turf, but we have a bunch of people that can have a look at what you do. And yeah, thanks for your attention. Just a quick word of conclusion also, because a bunch of things changed recently. As I said, STD-SIMD is going to be into C++ 26. Let's be frank, it was something I was very looking forward to at the beginning of the standardization process. Turns out the end product is less what it should have been, but whatever. I mean, if you want to have a taste of what we do, you can try and test the STD-SIMD. It's basically the same ideas. Names are different, API is different. Let's say that ours is better, but whatever. And what we want to do what we want and what we can do in Eve that the standard probably not gonna do is that we can be very aggressive about optimization. We can be very aggressive about API changes to get performances. That's one reason why in the end I was kind against the inclusion of STD-SIMD in the standard, because it's gonna fossilize the API. But it's a good idea to have a look at that if you want to see what kind of things we can do. Again, if you want to try out Eve and whatnot, don't hesitate. If you have any issue, you can ask us to have a look with you. Normally, documentation for starting up is actually okay. So if you have any issue, don't hesitate. And as I said, we are eager to have a look at different kind of application architecture. So we are always open to get better things in. Okay. So thanks a lot. And if you have any question, I will gladly answer them.
Okay, thank you, Joël, for the nice presentation. So there is no more question right now in the chat, but I'm pretty sure there will be at some point. So we just have to wait a bit. Maybe a first question, just to pass a bit of time. You said at the beginning that for vectorization, there is no standards, and that's a mess and it's terrible. But that being said, how do you choose to implement a feature or not, depending on the capabilities of the hardware? Do you want to have something which is common to everyone, or
so
the strategy?
What we try to do is to we do the following. Okay, let's take a very simple example. When SVE came out, they had a bunch of different way to handle masking, for example, than AVX2 had. So we are looking at it, and what we decided was to say that the SVE way of doing it is actually more wide and more abstract, cover more cases, okay? And the cases they handle natively were easily emulated in the other thing. So we upped the bar, and we say now we can do all of that. And if you have, how to say that? If you have to work on a system that doesn't have these specific things, we have a decent emulation. What we try to do is, whenever we have an intrinsics or a combination of intrinsics, we try to find it a home as a high-level functions. So for example, we have intrinsics we don't have. So for example, we don't have MM at sub, because it's an operation that doesn't make any sense on the wide, okay? And we purposely doesn't include it. Next to that, we have these compressed things that was very obscure operation that we walked back into a triplet of functions that make sense and then can use them. Okay. So usually what we want to do is that, is there something that provides the value as an algorithm or as a functions? And can we give it an actual decent high level semantic? And as soon as we have that, we fill in the blank. I mean, we are basically, what we do is basically polyfilling the intersection of every architecture's SIMD operations. We don't go by the lowest common denominator. But then, I mean, obviously, if you want to have the complex sublane masking FMAs that come from SVE2 on SSE4, it's not gonna fly in terms of performances, but we try our best to go as fast as we can.
Okay, so we do have some questions in the chat now. So question from Rothbeth, are there any possibility attempts so far to use Eve on GPUs?
Okay, short answer, nope. Longer answer, this is one thing I learned in my flesh, in my earlier. At some point, we had a tool that was basically doing this kind of things on the CMD, on GPU, on MPI, and whatnot, and so on and so forth. Turns out it turned into a mess to maintain. What took us weeks before took us months, then it started to cost us interns, and the latest features costed us PhD students. Okay, and in the end, it wasn't manageable. So our stance nowadays is that we split concerns. If do one thing good, it give you access to your CPU CMD registers. Give it and do it perfectly because that is one goal. We have other tools, okay, that start to try to fill in the blanks, and the overarching goal we have, so between Eve and the other tools, is to have a bunch of, how to say that, composable libraries that you can mix match to do whatever you want. Okay, and so if you want to have a array-based computation both on GPU and CPU, you can bring back all of that and do whatever we do. But we are very committed to have one goal per libraries. Okay, and I'm not even sure the programming model is correct on GPU, because the equivalent of what we do on GPU will be to have wide to cover over a warp or something like that, and then use internal low-level warp manipulation things to do whatever we need to do, and then use a simple synchronized operation on every lanes. But that's not sometimes that's not how you want to write your kernel anyway, if you want to be efficient. And that will be basically a bad reimplementation of CUDA cub that basically do this. So we went for something else. The same way we don't support a flexible sized register like on SVE. SVE has two modes. Either you fix the size, okay, right? Or you can let the binary decide at runtime what the size of your register is. And this breaks so many things that we didn't want to support it, because it's not SCMD anymore. It's basically vector computation, and that's another thing. Okay. So no GPU with Eve. That's not the goal.
Yeah, as you mentioned, of course, you can say a warp is a kind of vector register, but you have the block on top of that, you have the cluster on top of that, you have the grid on top of that. It's not tractable for.
If we were pre-CUDA times, where we were programming GPU as an actual multicore of pseudo SIMD instructions.
So maybe 206.
Yeah, but that's like backers 206 exactly. Where back in the day where we were doing matrix multiplication by pouring things into a texture and whatnot in OpenGL. But we evolved past that, so let's not go back into these trying times. So yeah, we are probably going to have another tool that take care of that. But even for GPUs right now, we are more akin to whenever we use them in other tools, we don't even go lower. As that low, we either use SQL or Thrust, because it's easier for us to maintain the code afterwards.
Okay.
I think we have another question.
Question from Henri Pierre. Do you experiment on real hardware or on emulators?
Depends. We have a decent x86 roster of actual machine for every x86 system we need. We have a bunch of ARM machines, but they are a bit old, so they don't do everything. But for ARM v7 and ARM v8 up to very recent system, it's okay. We do emulate on SVE because wink sponsors, we don't have an SVE machine at end. So if you happen to know where I can find one or have access to one, I'm okay with that. And RISC-V, we are currently running on emulators because we don't have the access. We need to find a way to get an actual RISC-SIMD vector extension enabled things. I think there is some that are planned to be released at some point. So we are probably going to have to see how we can do that. RISC-V at the moment, it's trying to support it. We have a bunch of a bunch of work being done, if I'm not mistaken. Where are you? Yeah, we have the basic things done. We have a long time ongoing things that we need to continue consuming. There's a bunch of functions from this PR we integrated, but this was, people that contributed that were a bit overeager. Whenever you want, okay, yeah, this kind of PR, if you see what I mean. So we extracted what we could from that, and it's integrated. There is a bunch of things that we need to test again, but we recognize RISC-V. We have the support for the registers. We have the basic load store, basic operation going on. We didn't have the opportunity to test if this is the optimal way to do things, especially because RISC-V has this funny, the register size is actually, it's a compound of two values and whatnot. So currently what we do, we take the smallest piece and we replicate it as much as we can. Should we do that? Should we have the middle size and go both way? We don't really know. Okay. And as long as we don't have an actual hardware, we can do bench on it. It's in the air, but we have the initial support for that, and that's something we want to push. But we need people a bit more knowledgeable in RISC-V that we are, and probably access to some hardware to get there. But this is on our roadmap. The same way we have a roadmap for WASM. WASM was kinda supported for a while, but they changed something recently and it broke all our tests. So we need to know what's going on. It's probably not us, but we need to dig into that. Okay, and as you may guess, we have only that much time a day, so we still have all of that to clean up. So yeah, we are going to get there. RISC-V is something we really want to have, and currently, what we're going to try to do is secure an actual machine and get from there. But it's definitely in the plan.
Okay, so another question from Henri-Pierre. Do you plan to support RISC-V vector extension v10?
The basics are there, but I'm not sure it's the best thing we can do, but it pass the test. So for now, it's I think they pass the test. Now that I say about that, let's have a look. But I think we do have the test. We do that 256 and 128 with whatever funny. So that's the classic one, and that's the one with the 16-bit first. So we do test them. So. It works. It's just that, this is emulated. And, oh no, everything is actually passing, maybe? 85. Oh no, okay, we don't test the algorithm yet and whatnot, probably because it takes too long to compile. Okay, we have a bunch of tests running out, basically whatever we have that works. So that's something we need to resume at some point. And this one is emulated for obvious reasons.
Okay, so there is no more question in the chat, so we'll try, it's important because you did some tricks and it's important to explain that. On your strlen, you are vectorizing the search of the length of your string.
Yes.
But of course, at some point you will overflow a bit on the allocated memory.
Yep.
And how it's possible that you don't get segmentation fault for that?
Because actually you can.
You can how it's possible? Explain why you can and why it's possible.
Okay, so
it's not really.
You are allowed to load a vector register that go over a bit of your memory, as long as you don't cross. You can always do it. Okay, as long as you don't cross a page boundaries, it's okay. If you cross a page boundary, it's a bit slower. It's very slower. And the only thing that is gonna complain when you do that is that if you use sanitizers, okay, because they see that you are going out of bounds, okay. But the OS doesn't give a crap about that because it is meant to be able to read a full-blown vector register out of a piece of memory. You are not allowed to write outside. Okay, you cannot write outside, but reading outside is fine. And so what we do is that we have this unsafe option that basically say, yeah, I know. I mean, I'm going out, but I'm allowed to. So please don't say anything to the memory analyzer or the sanitizer because I know what I'm doing. And then we use this to basically vectorize all algorithms without having to do the traditional, let's finish what remain into scalar modes. So it let us write pure Cindy code all over the data. And if we know that the data you read, in an algorithm are going to fit exactly, we skip that, okay? But if you don't know how many elements you have, you don't know their alignment, you can basically just read a full-blown vectors, and it's okay. The OS won't complain. The sanitizer will, because I will put some sentinels inside this interstice of the memory, but you are allowed to do that. Turns out it's hidden somewhere deep into the Intel documentation, and for the other architectures, we got like verbal confirmation from the people. It's not written anywhere, but if you look at what, for example, Esterlen on ARM does, it does exactly the same trick by overshooting the load. And so it's basically working everywhere. And the day it doesn't work on some architectures, we are going to find a way to hide that anyway. But yeah. And that's, for example, that's why, where is it? It's not there, but in the, where are you? In the, yeah, this one? Yeah. We load with a mask, okay? So we don't want to touch some places in memory. And basically, I mean, it's just used so that if you load outside, we know that we can skip the thing, okay? And so 99% when you load with a mask, it's just a load, because the behavior of load says that whenever you mask a load from memory, what you got into this line is undefined, and we went with a very efficient choice of, well, if it's undefined, you know what, it just loads the whole things because you are not entitled to read it. So, and that's why we have the ignore there, and there is going back there, so we cannot exploit them. And a lot of masking tricks on load is based on the fact that you can overshoot, you don't care about the value you put, so it's very efficient because we basically do nothing except shushing the sanitizer and whatnot. But yeah, you are entitled to do that. Okay? It's non-standard, obviously, but I mean, we are doing CMD intrinsic, so we are far beyond whatever the standard is meant to mean. So yeah, we go over with that. The same way that we have another trick where, for example, there is a lot of function where what you want to do to be efficient is basically playing around with the bits of your values, okay, right? And so we use the fact that for the compiler, every CD register is bitwise compatible with the other, and we just bitcast the register into one another just to get the bit, do the operation, and send it back. And for example, on SSE2, you don't have vectorized intrinsic for absolute value for floats. And so what we do is that we take the float, we bitcast it into an integer, and we smoosh the bit sign, and we put it back into a float. And all the bitcasts are no-op, so you just see the compiler putting a mask over a register of float, and it goes, okay, that's fine, I know how to do that. So we are in the implementation, we are in a place where a lot of ugly tricks become useful again, and then you have to actually use that for having performances. Another cool trick, if I have like 5 seconds on that. Yeah, where is let's do a simple thing there. Yeah, there is a bunch of use cases, especially in, let's take an integer, especially in image processing, where you want to increment or decrement the value conditionally, right? And so you can have stuff like that. So let's do it this way. So logical is our type that says that you have a mask, something like this, right? And so you could say, okay, I want to increment v by 1, okay, if where the mask is true, actually, okay. And so you can say, okay, so if the mask is true, okay, you can do something like if else the mask is true, then I do v plus 1, and if not, I return v. Okay, I don't do anything. Okay, and so we in SSE2 we end up with this bunch of things. Okay, because there is no if else, you just have masking and squishing the bits. It's a bit better. What are you doing? Oh yeah. Sorry about that. Probably need to do this. Should I? Could I? Yeah. So we have the comparison, and then we do a blend and whatnot, okay? And they all look the same, okay, right? Except this is actually slow by 1 or 2 cycles. It's actually adding 1. Now, let's go deep into high-level math, okay, right? Plus 1 is actually minus 1. Everything is okay with that? And that's a cool thing, because you know what? What's a SIMD logical mask, actually? It's a bunch of 0 and 1, like a bit of Boolean, right? Except it's all zeros or all ones, which means that whenever my value is true, if I look at the mask as an integer, not as a Boolean, whatever, it's actually minus 1. So we can actually optimize this by knowing that. But if else don't know about it, it cannot deconstruct whatever is that. So that's one reason we have this. That's one reason we have this thing like we have the increment function. Okay, why do we want to have that? Well, because we can actually put a mask on it. And now I have the API to find about that. Okay, what did I think? Oh yeah, what about semicolon? Important things. Now I know I'm trying to increment with the mask an integer, so you know what? I'm taking the mask, I'm doing the subtraction. And that's the correct way to do that. And we have the correct code in terms of performances, in terms of whatever is going on there. I mean, we can check the other one, okay? And you see that the compiler didn't know the joke about it. We have to tell him, okay? And we have the best looking code when we use the highest level API. And the whole API of Eve is made like this. If you want to do a high-level operation, you have to fetch the high-level operation we provide, because it encapsulates all those low-level SIMD tricks that came back from the 90s and that people forgot about. And I was thinking about the fact that those tricks were actually very, sometimes look like magic, and we keep finding some where just so you have an idea of that. Where is it? Where are you? Oh, did we do it already? Oh yeah. Yeah, you have an integer. You have an 8-bits integer. You want to convert it into float. Well, the way to do that up to very recently was to say, oh, you take your integer 8 bits, you convert it to integer 16 bits. There is an intrinsic for that. And then to integer 32 bits, so 2 calls. And then you convert to a float. And as your value is 8 bits, it always fits into the float. So you just have 3 conversions to do. You get there, okay, right? Except it's not 3 conversion. I mean, it's 3 conversion, but it's like 2, 6, 14 operation. Because every time you go up a level, you have more and more vectors to take care. Well, turns out, you know how you turn an 8-bit integer into a float? You take your 8-bit integer, you put it at the end of the mantissa bits. Okay? As an integer, you put the bit there. Then you turn it into a float. You subtract the 2 to the power of 23 things. Okay? And what's left? Well, you have an empty exponent, whatever mantissa before. You have the smallest exponent you can get, and your bits over there are exactly your integer things. Okay. Yeah. Somebody found out about that last year. So there's plenty of tricks like this. And what we try to do is that people need to get there to get the performances. And so we do all those tricks, as a hidden box, so you don't have to think about it. And so, we do that a lot. So the load tricks, the fact that whenever we can, we can say, okay, we don't care. The fact that we abuse the bitwise equivalency between the register, all of that is made so that we can get to the correct level of performance.
Okay, or maybe 2 questions on masking, and then we will call it a day or a morning at least. Once you are using the masking on the load, so you load a vector and you mask to be sure that you don't load crap. Usually, once you use a compiler and you try to vectorize with the auto vectorization, you get a pill and a tail. So does it mean that you don't need them, or it's hidden under the hood?
We don't do tail.
Okay,
we do zero head and tail endings. Everything is we start from vectors to vectors, and that allows us to do some things that, for example, the standard didn't think about. We can have non-templates lambda function inside our algorithm because we only ask for a function that consumes a while. Most of the time, if you look at other libraries that do this, either you have to pass polymorphic lambdas with auto because it will call the same lambda both on the scalar and on the whatever register you use, or you need to have manually clean up the tail. Okay, and so we don't do tails. There is no tails handling anywhere. It's just like we just woof everything as regular things, and it also implies that we have a non-trivial amount of logic to deduce as soon as you have multiple input and output algorithms. Like, for example, transform, you have 2 input, 1 output, which means that if you wanted to be efficient with the tail handling, you should know by how many every of those are, misaligned, to know how many head you need to do before you are in the position where everybody is aligned, and stop far earlier because you need to stop where the first one stopped being aligned. And so you have to do some complex computation. What we do is we just unalign load everything, and we just run over the tail with the load masking things. And the logic is far simpler, and I think we measure that we are like 15-20% faster than the one with the tail sometimes on some algorithms. So we just run with it because it's just easier to implement. You don't have to do all these complicated, like plus n minus m divided by p whatever, And so all the code is actually simpler to write. The compiler is able to see through it far better. So sometimes we have surprises because the compiler make a pass over what we did, and it slightly change the thing. So it's easier for him to see what the intent is, and it goes over some additional optimization. So we do no tails. I think if you want to have a deep look at the algorithm design, we have a video about that where we go over all this, tail handling and whatnot. This one also maybe. But yeah, we basically just, there is no tail. Everything is just a bunch of data, and we use the fact that we can roll over to get there.
Okay. And once you're using the masking with numeric, for example, do you need to also change the compilation options, to use a kind of denorm flush to 0, for example, or you don't need it because it's automatic in your library?
It's not what we do, actually. Depending on the algorithm, sometimes basically, for example, for the min and max, there is a trick where you can get away with not ending the NaN by reordering the comparison you do for selecting the min and the max. So sometimes the numeric version is just a different algorithm that is like NaN impervious, if I can say. And for the other one, most of the time, either we do the obvious thing, which is masking the lane where LISN is true, and it doesn't cost us much. Or some architectures have intrinsics for exactly doing this, like doing some operation and clearing up the NaN, or actually clearing up whatever value you want that match some kind of floating point classification things. AVX512 have that. You can mask over nans, the normal, infinites, negatives, whatever. And it's just an enum in the intrinsic. So this one we do it a lot. And we don't rely. We make the assumption that if you change the whatever, like floating point operation option at the compiler level or at runtime, we don't care. I mean, at runtime we cannot anyway know about that because it's runtime, and at compile time, I mean, we just go with the flow. That's why, for example, every time we test for precision and so on, we have our own very specific precision tests that is actually done with, computing how many actual bits of difference we have, so we can be rather independent of whatever the floating points option there is. I mean, we don't do any specific how to say that assumptions about rounding modes and whatnot, because if not, I mean, it's just doesn't work because we cannot have access to whatever the option is. So sometimes we have a bunch of functions that we use internally that force the computation to be a bit accurate with extra precision, so we know we have all the bits we need whatever the guy decided. Okay? And those slides into these EEE helpers that we have at some point. Because sometimes whenever you want to do very precise operation, especially on float, I mean, when you have a vector of float, you have a vector of float. You don't go into the special extra precision mode and whatnot. And so sometimes you may lose precision, and so to gain it back, sometimes we have, especially in the pedantic mode, we have an extra step that do this extra precision computation and do some correcting on the results. So either it's free because the algorithm changes when we see that we have the numeric or the pedantic, however, options. And when it's a bit more complicated than that, we usually have function-specific optimization to get rid of them. But we don't use the FE states or whatever, because it's too unreliable to be portable for what we do.
Okay, so see, if I use Eve and in my compiler options I forget to remove the flush denorm to 0, I had to remove it because you take care of that.
Yeah,
Maybe
I mean, normally, yeah, I mean,
yeah.
I mean, you can put numeric on the functions that do. On other architectures, for example, PowerPC, you do have that by default, because you are not allowed to have the normals in semi-register on some variation of PowerPC. And so that's also why we have a bunch of, I didn't think about that. We have a bunch of, where are they? Yeah, we, oh no, it's not PowerPC. Oh, maybe it's ARM. I don't remember. Okay, one of those architectures. I remember putting it, but I don't remember where. Maybe it's old style Neon. Yeah. If you are on ARM 7, you don't have the normals into registers. They are not supported. Okay, so we have these special things, and this actually triggers. Where is it? Cleaning up the thing I should do. Or is it? No, it should be somewhere like there. Okay, there is a platform file. I know that it is how it's called. Platform, yeah. Okay. And these things basically gather all those no-nans and whatnot. So we detect fastmat. We detect a bunch of functions like this, and we turn that into context per flags that we can use into the function. Yeah, we have this kind of funny things, for example, and know the normals. And depending on what we defined, okay, and find out about, we have those things. And so, for example, stupid things. I mean, let's take the mean numeric. Mean numeric, the first thing it does, okay, you want to do numeric, but you tell me you don't have nans. You know what? Let's just do a mean, because it's always good. Okay, so we use this information into our if context per web to simplify the implementation and whatnot. So we do detect, but we detect what we can detect, which is basically compiler option and whatnot. Yeah, it's probably an ABI. I think it's an ABI. Yeah. I kind of wrote that, but it doesn't look so. Okay. Yeah. We do the detection of that and whatnot, and we do all those things. So yeah, we have these systems, but unless the function actually has any optimization we can get from that, we just don't care about them, because usually it doesn't apply to whatever we are doing.
Okay. Okay, I have a last question for you, and then we'll stop. So you mentioned that a bit in the beginning of the presentation, but it's always better to show the assembly.
Yeah.
Once you use sines and cosines with specific quarter of the unit circle, that's really powerful, and I think a lot of people will be interested in that. Yeah.
Let's find a place to do this, or let's do it this way. Okay, let's put that into the fridge. So we need math, apparently. No math. So yeah, so float is probably enough.
The idea is to show you the difference between a cosine and sine call without any optimization and a cosine and sine assembly. Once you say, okay, I'm pretty sure I just want this quarter of a circle on this part of the circle, unit circle, and stuff like this. So you will see the difference is really huge. It's important also to have that.
Yeah. But now I need to. I probably need to do some that. Okay. The implementation changed recently. So where are you? Okay. So basically, when you know that your angle is what is that? This quarter of the circle as the minus p over 4, p over 4, something like that. No. Yeah, I mean the quarter circle is p over 2. Okay, I mean you take a quarter circle but you put it on over the zero things. You actually have a very simple polynomial interpolation for that. It's like well, maybe we can actually this one should work. It's easier if you see the FMAs. Okay. So recently, the kernel for cos and so on get no inline because they were causing too much compilation time. So yeah, you have like 1, 2, 3, 4 FMAs, and then we do the cleanup. But sometimes you need more than that. You need like half the circle. Okay, so you have another options. So if you are outside this, you get none. Okay, if you are outside the quarter circle, you get none. So now if you are in the half circle, we need a bunch more FMAs, like a bunch more. Okay. And then we start having more blends to select the part we need. What actually happens is that when you do the half circle, the first thing we do is that, are you in the quarter circle? Because I know how to do that. And if you're outside, I'm just adding up what you need to be adding up. And then we have what? Full circle. So you need to be between 0 and 2 pi, exactly. Okay. This one is also a mouthful. Yeah, it starts to be, it starts to be a bit bigger. And you don't know what you have. You have a range, a random assortment of. So what you can do is just call cos. And cos do a thing which is gonna try to filter out your values and to check, are they all in the quarter circle? If yes, I call the quarter circle. Or are they all beyond the half circle or the full circle? And if not, I'm calling a huge thing. So, and you can actually see them. Okay, so this is quarter circle. Okay? This is half circle. This is full circle, and this is the do whatever you need to do to get an actual cosinus running. Okay. And basically, what we do, if we go there, yeah, we go into these things, and these things basically, they test different ranges and they jump. Okay. Now the difference is, if you are in AVX2 float, so you have like 8 floats per registers, the speed up of this one compared to STD cos okay, is about 6 point something. Okay? It's a bit less than 6. Okay. And as soon as you go lower in terms of range, as you compute far less things than the standard, I mean the quarter circle cost on AVX2 floating point, 32-bit floating point. I mean, the standard cost is about 50 to 65 cycles. And the quarter circle cost on floating point AVX2 is about like 7. Okay. And so in 7 cycles, we compute all these things, okay, all these 8 cosinus. Okay. So obviously, sometimes you don't know, so you are going to go through the big functions. But as soon as you know information about your data set, we have those options to basically, go there instead of going into the mammoth at the end. And and it's going just to go faster. Okay, and this one is probably big also. This is a big thing. The math we use for the interpolation is based on some kind of Remez algorithm to find out what the exact polynomials is. For some others, we find a paper by, I don't remember what his name. Well, basically we compute some kind of a mix between two functions, and then depending on if you look at the odd or even parts of the vector, you have one or the other results, and so you can reconstruct them. Stuff like that. All the exponential also use a proper efficient interpolation scheme and so on. Yeah. And so, bam, it's like 1, 2, 3, 4 FMAs. Oh yeah, and we have this monster in FX 512 that do the ternary switch, and so on. And so, yeah, we have this ability to combine and construct those algorithms. And usually what we do is that as soon as we see that there is something we can optimize, but it's not something people want all the time, try to turn that into a reusable options. The one over the trigonometrics are very specific because they only make sense with trigos, but the other tries to be a bit more general.
Okay, thank you, Joël, for the
Thanks.
presentation, for all the answers. So thanks you everyone for attending this webinar. We will do some magic with Python next week on CPU. We'll start gently on CPU and go on the GPU after. And have a good day and see you next week. Bye.
See you.